Here is the uncomfortable fact. Light carries energy, transfers momentum, and can heat, push, and power reactions, yet it has no mass. If you've ever heard E equals mc squared, this should feel like a contradiction hiding in plain sight, a misunderstanding that shows up in every E equals mc2 explained video. Tonight we'll unpack it with calm precision, following photon energy into the real meaning of mass, rest energy, and why photon mass is the phrase that traps so many explanations. We'll move from everyday intuition to modern relativity and quantum fields, so massless particles stop sounding like a loophole and start sounding like a rule. You and I will move forward one careful step at a time, allowing the picture to settle clearly until it becomes natural to see how the universe allows photons to carry energy without carrying rest mass. And we begin with part 1. If photons carry energy, why doesn't the universe let them have mass? Light can heat metal, push spacecraft, and free electrons from atoms, yet physics continues to describe light as having no mass. At first glance, those two facts seem hard to place side by side, and that tension is exactly where many familiar misunderstandings begin. Instead of forcing a quick conclusion, we can take a moment to look more carefully at how these ideas are actually used in experiments. Photon energy is something laboratories and observatories measure every single day with remarkable precision. Photon mass, by contrast, usually enters the conversation only when E equals m squared is treated as a convenient shortcut rather than as a statement with very specific conditions. A good place to begin is with a mistake that feels almost natural. People hear energy and mass are equivalent, and they translate that into anything with energy must have mass. But E equals m squared does not say that. It says something narrower and more precise. A system that has mass has an associated energy even when it is at rest. That is why physicists often call it rest energy. If an object can be at rest, you can talk about its rest energy, and then E equals mc squared tells you how mass and rest energy are tied together. A photon is the one familiar thing in physics that refuses to sit still in any frame, even as a thought experiment. That single fact changes everything. Long before Einstein wrote E equals mc squared, light was already showing hints that it behaves unlike matter. In the 19th century, James Clerk Maxwell wrote down the equations that unify electricity and magnetism, and out of those equations came a wave speed that matched the measured speed of light. That was more than a coincidence. It suggested that light is an electromagnetic wave, and that its speed is set by the properties of space itself, not by the motion of the source. Once you accept that, you are already standing near the edge of special relativity, whether you realize it or not. Then the 20th century arrived with experiments that made the situation sharper. The photoelectric effect showed that shining light on a metal can eject electrons, and that the details depend on the light's frequency rather than just its brightness. Einstein's explanation, in the 1900s, treated light as coming in discrete packets, photons, each carrying energy proportional to frequency. The energy was not a metaphor. It was an accounting tool that predicted real voltages and real currents. And from that point on, photon energy stopped being a concept and became a measurable, testable quantity. If photons carry energy, they also carry momentum. That sounds strange at first, because momentum is often introduced as mass times velocity. But physics does not give photons a pass here. Momentum is more general than that simple beginner formula. For light, the momentum is linked to energy by a relation that becomes essential in everything from laser physics to astronomy. Once you accept that photons have momentum, a cascade of consequences follows, and the universe repeatedly confirms them. One of the most direct confirmations is radiation pressure. Light exerts a force when it is absorbed or reflected. This is not a modern claim. It was studied in carefully designed experiments long before spaceflight. But spaceflight made it impossible to ignore, because sunlight can act as propulsion. A solar sail works precisely because photons transfer momentum to a reflective surface. NASA has long treated solar sailing as real propulsion, and the technology has been demonstrated in practice. A clear example is the Icaros mission, launched in 2010, which demonstrated acceleration by photon pressure and attitude control using a deployed sail. The force is small, but it never stops, and in space, a tiny continuous push becomes meaningful. Now notice what that means. Photons behave in ways that sound like massive behavior, force, momentum transfer, energy delivery, yet their speed never changes. You can add more photons and increase the pressure. You can increase frequency and increase energy per photon. You can concentrate light and raise temperatures. But you cannot slow a photon down in vacuum the way you slow a thrown ball. That difference is the heart of the puzzle. This is where E=mc² becomes dangerous in careless hands. A common mistake is to take a photon's energy E, divide by c², and announce a mass. The arithmetic produces a number, so it feels legitimate. But physics is not asking for a number. It is asking for a definition. What kind of mass are we talking about? Rest mass or something else? In modern physics, the mass that matters most is invariant mass, also called rest mass. It is the same in all inertial frames. It is not how heavy it feels while moving, and it is not energy divided by c². It is a specific property of a system's energy and momentum taken together. When you define mass properly through relativity's energy-momentum relationship, a photon lands at a clean result. Its invariant mass is zero, not almost zero. Exactly zero in the theory, and consistent with every test we have ever performed. Einstein himself disliked introducing confusing mass concepts for moving bodies. In a letter to Lincoln Barnett dated June 19, 1948, he wrote, "It is not good to introduce the concept of the mass. It is better to introduce no other mass concept than the rest mass, m." That remark is often quoted in discussions about relativistic mass, but it also points to why the photon case becomes so tangled. If you try to force mass to mean total energy, you will start assigning mass to things that cannot have a rest frame, and the concept stops doing its job. The rest frame is the silent requirement behind E=mc². For an electron, a proton, a cup of water, or a spacecraft, you can always imagine a frame moving alongside it where it is not moving. In that frame, the object has energy even with zero kinetic energy, because it still has rest energy. That is where the m in E=mc² lives. A photon never grants you that frame. If you try to move alongside a photon, special relativity tells you what happens. You need to move at the speed of light. But any object with non-zero rest mass requires infinite energy to reach that speed. So the photon rest frame is not just hard to achieve, it is forbidden. There is no viewpoint from which a photon is at rest, and therefore there is no rest energy to assign in the usual way. The photon has energy, but not rest energy. It has momentum, but no invariant mass. This may still feel unsatisfying unless the universe gives you a reason to trust it beyond definitions. It does. If photons had even a tiny non-zero rest mass, electromagnetism would change. The structure of electric and magnetic fields would be altered at large distances. The way radio waves propagate would shift. Planetary magnetic fields and interplanetary plasma behavior would not match what spacecraft observe. That is why physicists treat photon mass as something you can constrain experimentally. Modern constraints are extremely tight. Reviews and compilations, such as those associated with particle data group summaries, quote, upper limits at the level of about m, gamma is less than 8. 4 times 10, negative 19 eV, c, 2, corresponding to roughly 1, 5 times 10, negative 54 kg. Even if you do not memorize those numbers, the message is clear. If the photon has rest mass, it is so small that it has never revealed itself in any confirmed observation. Astronomy adds another layer of testing. If photons had rest mass, the speed of light in vacuum would depend slightly on frequency. Over long distances, that would produce arrival time differences that would accumulate. Telescopes that observe distant sources across wide wavelength ranges would see distortions in timing and propagation that do not match massless light. Instead, what observatories see is consistent with massless behavior across enormous travel times. It is also worth noting that some of the most sensitive astronomical instruments are designed around photon energy accounting with extreme precision. The James Webb Space Telescope must keep its instruments cold so that the telescope itself does not flood its detectors with its own infrared emission. NASA describes Webb's operating temperatures as stable, below about 50 K, with the near-infrared instruments around 39 K, and ESA reports that MIRI, Webb's mid-infrared instrument, reaches below 7 K. Those numbers matter because they show how seriously modern astronomy treats photon energy. The telescope is engineered so that a few stray thermal photons do not overwhelm the signals from the early universe. So, photons carry energy and momentum in ways that are practical, engineered, and measured. Solar sails feel photon pressure. Infrared detectors count single photons. Spectrometers measure photon energies by the fingerprints they leave in matter. And yet, the invariant mass remains zero, because mass is not energy in general. Mass is the kind of energy a system still has when it can be at rest. A historical example can make this distinction feel more concrete. In 1923, Arthur Compton studied how X-rays scatter off electrons. The scattered X-rays changed wavelength in a way that depended on angle, and the effect made sense only if you treated light as carrying momentum like a particle. Compton's result did not assign rest mass to photons. It showed that photons carry momentum while remaining massless, and that energy and momentum can be traded between light and matter in a way that conserves both. The photon does not need mass to behave dynamically. It needs energy and momentum, and relativity already has a place for that. This brings us back to the hook with a cleaner set of questions, the kind that keep the mind engaged without forcing it to strain. If photons can push a sail, why do we ever associate pushing with mass? If photons can deliver energy, why do we assume energy must always come with rest mass? If E equals mc squared is real, why does it feel like a contradiction when we apply it to light? The most plausible answer is not that the universe is inconsistent, but that we have been using a single equation as if it were the whole story. Because E equals mc squared is one face of relativity, not the entire structure. In the full structure, energy, momentum, and mass are connected in a way that keeps the photon case perfectly consistent. Photons have energy and momentum, but no rest energy, and therefore no invariant mass. That is why light does not escape the rule. It follows the rule so strictly that it is forced to be massless, and that conclusion has a consequence that is harder to ignore than the photon itself. If mass is tied to rest energy, then the mass of familiar matter is not simply the sum of the masses of tiny pieces of stuff inside it. It is tied to internal energies, bindings, and fields in ways that most people never learn in school. The moment you accept that photons carry energy without mass, the next tension becomes almost unavoidable. When you pick up an object and feel its weight, what part of that weight is actually matter, and what part is energy wearing a stable shape? Part 2. What is mass really, if most of your body isn't made of matter? What if nearly all the weight you feel when you stand on a scale has almost nothing to do with the particles you imagine filling your body? That idea sounds implausible at first, almost offensive to common sense, yet it is one of the most carefully tested conclusions in modern physics, and it forces us to confront a quiet misunderstanding that has followed science for centuries. For most of human history, mass was treated as a simple concept. Heavy objects contained more substance than light ones. Stones weighed more than feathers because they were made of more material. Even Isaac Newton, who formalized mass with extraordinary precision, described it as a quantity of matter proportional to density and volume. That definition worked beautifully for everyday mechanics and for astronomy as it was practiced in the 17th and 18th centuries. Planets orbited, projectiles flew, tides rose and fell, and the mathematics of mass as substance seemed complete. The trouble began when physics looked inside matter itself. By the early 20th century, atoms were no longer abstract points but structured systems, with electrons moving around dense nuclei. As soon as scientists began to measure the masses of these components, something unsettling appeared. If you add up the masses of the electrons, protons, and neutrons that make up an atom, you do not get the mass of the atom, you get less. Sometimes much less. This was not a rounding error, it was systematic. When nuclei form, mass goes missing. In nuclear reactions, mass disappears or appears in exact correspondence with released or absorbed energy. Einstein's equation provided the bookkeeping rule, but it did not explain the deeper meaning. If mass can vanish into energy, then mass itself cannot simply be matter. It must be something more subtle. Albert Einstein was deeply uneasy with the traditional definition of mass as amount of stuff. He knew it was useful, but he also knew it was incomplete. In his writings and correspondence, he repeatedly emphasized that mass is a form of energy, not a separate substance. In a letter from 1948, he warned against attaching too much physical intuition to the word mass itself, noting that only rest mass had a clear and invariant meaning across frames of reference. As experimental tools improved, this discomfort became unavoidable. Particle physics made the problem sharper, not simpler. Protons and neutrons, once thought to be elementary, turned out to be composite objects made of quarks, held together by the strong interaction. When physicists at facilities such as CERN began to measure the masses of individual quarks, the numbers were startling. The up and down quarks inside a proton contribute only a few % of the proton's total mass. The electron contributes almost nothing by comparison. This means that if you disassemble a human body conceptually into its fundamental particles and add up their intrinsic masses, you recover only a small fraction of the mass you started with. Well over 90% of the mass of ordinary matter does not come from the rest masses of quarks and electrons. That statement is not philosophical. It is quantitative and supported by decades of measurements in quantum chromodynamics, the theory that describes the strong force. Where then does the rest of the mass come from? The answer is energy, but not in the vague sense of activity or motion. It is energy stored in fields, interactions, and confinement. Inside a proton, quarks are bound together by gluons. These gluons are massless, much like photons, yet they carry energy and momentum. The quarks themselves move at relativistic speeds inside the proton. The strong force field is intense and dynamic. All of this contributes energy to the system, and because the proton can be at rest as a whole, that internal energy appears as mass. This is not speculation. Lattice quantum chromodynamic simulations, run on some of the most powerful supercomputers in the world, reproduce the observed masses of protons and neutrons from first principles. They do so by calculating the energy stored in the strong interaction fields and the motion of quarks, not by inserting large intrinsic masses by hand. The agreement between simulation and experiment is one of the great successes of modern physics. NASA and ESA do not directly study quarks in space, but they rely on this understanding every time they model nuclear processes in stars. The energy that powers the Sun comes from nuclear fusion, where small differences in mass between reactants and products are released as energy. When hydrogen nuclei fuse into helium, the helium nucleus has less mass than the original protons. The missing mass appears as radiation and kinetic energy. That conversion keeps the Sun shining and has been confirmed by solar neutrino measurements and stellar models refined over decades. The same principle applies, quietly and relentlessly, inside every atom of your body. The mass you attribute to your arm or your chest is not sitting there as tiny solid beads. It is largely the energy of fields and interactions frozen into stable configurations. Matter is energy arranged in long-lived patterns. The Higgs field adds another layer, but it is not the whole story. The Higgs mechanism explains why certain fundamental particles have non-zero rest mass at all. Electrons and quarks interact with the Higgs field, and that interaction contributes to their masses. This contribution is essential, but it is small compared to the total mass of composite objects like protons. The Higgs field gives particles the ability to have mass. The strong interaction gives most ordinary matter its weight. This distinction is often blurred in popular explanations, but it matters. When the Higgs boson was discovered at CERN in 2012, confirmed by experiments using detectors like ATLAS and CMS, it was rightly celebrated as a triumph of the Standard Model. Yet even physicists were careful to emphasize that the Higgs field does not explain most of the mass of everyday objects. It explains why quarks and electrons are not massless. The bulk of mass still arises from energy bound by forces. Carl Sagan often reminded audiences that science is not just a body of knowledge, but a way of thinking, a discipline of humility before nature. In his series Cosmos, he described how matter and energy are deeply connected, not as abstractions, but as measurable realities shaping stars and people alike. He did not romanticize this connection. He treated it as a fact with consequences. One of those consequences is that the word matter becomes less solid the closer you look. If most of your mass comes from energy stored in fields, then the boundary between matter and energy is not sharp. It is a practical distinction, not a fundamental one. This realization does not dissolve objects into mysticism. It anchors them more firmly in physics. Consider a simple comparison. Heat a block of metal. Its temperature rises because the atoms vibrate more vigorously. That extra internal energy increases the total energy of the system. In principle, it also increases the mass by an amount given by the energy divided by the square of the speed of light. The effect is far too small to measure on a household scale, but it is real. The equations do not care whether the energy comes from nuclear binding or thermal motion. If the system can be at rest, internal energy contributes to mass. This perspective explains why photons, discussed in the previous part, do not acquire mass simply by carrying energy. A photon does not have internal energy in a rest frame because it has no rest frame. Its energy exists entirely as motion through spacetime. By contrast, a proton at rest contains enormous internal activity. Quarks race, gluons bind, fields fluctuate, yet the system as a whole can be still. That stillness is what allows energy to appear as mass. Historically, this shift in understanding was not immediate. Even in the mid-20th century, many physicists spoke casually of relativistic mass, treating energy and mass as interchangeable labels. Over time, that language faded, not because it was forbidden, but because it obscured more than it revealed. Modern physics prefers invariant mass because it keeps track of what does not depend on the observer. This preference is not pedantic, it prevents errors. If you define mass as total energy, you would say that a hot object weighs more than a cold one, which is true in principle. But you would also say that a fast-moving object has more mass simply because it is moving, which leads to confusion when comparing different frames. Invariant mass avoids this trap by tying mass to rest energy alone. When you apply that clarity to the human body, the result is quietly astonishing. The solidity you experience is not due to a dense packing of massive particles. It is due to electromagnetic repulsion between electron clouds, nuclear forces locking quarks into protons and neutrons, and energy trapped in stable arrangements. The scale reads a number that reflects all of that energy, not a pile of material in the naive sense. None of this diminishes the reality of matter. Tables do not become illusory. Bodies do not become unreal. Instead, reality becomes more layered. What you touch is the macroscopic expression of fields and energies behaving consistently over enormous numbers of particles. That consistency is what gives rise to weight. Modern observations reinforce this picture from unexpected angles. In astrophysics, the mass of neutron stars far exceeds what you would expect if you treated them as collections of neutrons with fixed masses. Their extreme gravity compresses matter into states where interactions dominate completely. The mass of a neutron star reflects the balance of energy, pressure, and space-time curvature. ESA's observations of pulsars and NASA's measurements of gravitational waves from neutron star mergers confirm models where energy and mass are inseparable at a fundamental level. Even at cosmological scales, mass is not just stuff. Dark matter, whatever its microscopic nature, reveals itself through gravitational effects. Its mass influences galaxy rotation curves and large-scale structure, yet its composition remains unknown. This uncertainty underscores the lesson rather than undermines it. Mass is a property inferred from energy and gravity, not a direct count of particles we can hold in our hands. So when you ask what mass really is, physics does not give a single-sentence answer. It gives a framework. Mass is the measure of a system's rest energy. That energy may come from particle interactions, field configurations, confinement, or binding. Matter is one way energy organizes itself, but not the only one. This understanding also sets the stage for what follows. If most of your mass is energy held together by forces, then changing those forces would change mass itself. That idea is not hypothetical. It plays out in nuclear reactions, in particle decays, and in the early universe. It raises questions about how mass emerged as the universe cooled and structures formed. From there, the tension moves forward on its own. If mass is not primarily substance but energy stabilized by interaction, then what decided which interactions would give matter? Part 3. Why energy, not matter, is what we've been weighing all along. What if every scale ever built has been telling the truth, yet almost no one noticed what it was really saying? When you step onto a scale and see a number appear, it feels like a direct statement about how much matter your body contains. But physics has been quietly rewriting that interpretation for more than a century, and the evidence now points in a direction that is both precise and unsettling. The scale is not weighing matter in the way our intuition imagines. It is responding to energy that has settled into stable forms. Albert Einstein understood this shift earlier than most, and he was careful about how he described it. In his original work on relativity, he did not say that matter turns into energy as if one substance becomes another. He showed that mass itself is a measure of energy when a system is considered at rest. The language matters. A resting system can still contain enormous internal activity, and it is that internal energy that reveals itself as mass. To see why this matters, it helps to return to the atom, not as a symbol, but as a physical system that has been measured again and again. An atom consists of a nucleus surrounded by electrons. The nucleus itself is made of protons and neutrons. When physicists measure the mass of a nucleus and compare it to the combined masses of its individual protons and neutrons, they find a discrepancy. The nucleus weighs less than its parts. The missing mass is not lost. It appears as binding energy released when the nucleus formed. This was not discovered in a single dramatic moment. It emerged gradually through careful experiments in nuclear physics during the early 20th century. As scientists measured nuclear reactions with increasing precision, they saw consistent patterns. When nuclei bind tightly, energy is released. When they are forced apart, energy must be supplied. The mass difference tracks this energy exchange exactly in accordance with Einstein's equation, interpreted correctly. Binding energy is not an abstract concept. It is the reason nuclear power exists. It is also the reason stars shine. In the core of the Sun, hydrogen nuclei combine to form helium. The helium nucleus has less mass than the 4 protons that went into it. The difference appears as energy that eventually reaches Earth as sunlight. NASA's solar models, refined over decades and confirmed by neutrino detectors, rely on this mass-energy accounting to explain the Sun's luminosity and lifetime. But the story does not stop at nuclear scales. Even chemical bonds involve energy, and that energy contributes to mass in principle. When atoms form molecules, they release or absorb energy, depending on how the electrons rearrange themselves. The effect on mass is extremely small, far beyond what laboratory scales can detect, but the principle remains the same. If a system can be at rest, then its internal energy contributes to its mass. This is where the idea of mass as confined energy becomes unavoidable. Matter is not a passive collection of particles sitting quietly in space. It is a dynamic arrangement of fields and interactions held in stable patterns. Inside a proton, quarks are bound by the strong force, mediated by gluons. The quarks move at speeds close to that of light. The gluons themselves are massless, yet they carry energy and momentum. The strong interaction field is intense and constantly active. All of that energy is trapped inside a system that, as a whole, can be at rest. The result is mass. Modern quantum chromodynamics makes this picture quantitative. Supercomputer simulations that discretize space and calculate the behavior of quarks and gluons reproduce the observed masses of protons and neutrons without inserting large intrinsic masses by hand. The bulk of the mass emerges from energy associated with motion and confinement. This is not an interpretation layered on top of data. It is the data, expressed through theory and computation. Carl Sagan often emphasized that science progresses by replacing familiar stories with better ones, not by stripping away meaning, but by grounding it more firmly in evidence. The idea that mass is energy confined into stable structures is one such replacement. It does not make the world less real. It makes it more intelligible. Consider how this perspective changes the meaning of everyday measurements. When you weigh an object, you are measuring how strongly it resists acceleration under gravity. That resistance is proportional to its mass. But the mass, in turn, reflects the total rest energy of the system. The scale does not care whether that energy comes from particle masses, binding energies, or internal motion. It responds to the sum. This is why heating an object increases its mass in principle. As temperature rises, the internal energy of the system increases. The atoms vibrate more vigorously. The total rest energy increases slightly, and so does the mass. The effect is tiny, but it is real, and predicted by relativity. Physicists do not usually mention it because it is far below practical measurement limits for everyday objects. But in high-energy systems, the effect becomes important. The same logic explains why compressed systems weigh more than relaxed ones. Again, in principle, energy stored in compression contributes to rest energy. The scale, if it were infinitely precise, would register the difference. This is not poetic language. It is a direct consequence of how mass is defined in modern physics. Einstein was aware that this view of mass would be counterintuitive. In his later writings, he stressed that mass should not be treated as a substance, but as a property of energy in a specific condition. He resisted attempts to reintroduce substance-like interpretations because they obscured the role of internal dynamics. Mass is not what something is made of. It is what energy does when it is trapped. Astrophysics provides some of the clearest confirmations of this idea. In neutron stars, matter is compressed to extraordinary densities. The energy associated with degeneracy pressure, nuclear interactions, and relativistic effects becomes dominant. The mass of a neutron star cannot be understood by simply counting neutrons. It reflects the balance of energy and gravity in a system pushed to its limits. Observations of neutron star mergers by gravitational wave detectors, supported by NASA and ESA follow-up observations across the electromagnetic spectrum, match models where mass is deeply intertwined with internal energy. At even larger scales, the same accounting governs the structure of galaxies and the evolution of the universe. When cosmologists talk about mass density, they are often talking about energy density expressed in a form that gravity responds to. The distinction between matter and energy becomes less rigid. Both curve spacetime. Both influence cosmic expansion. The equations do not privilege one over the other. This perspective also clarifies why earlier attempts to explain mass purely in terms of matter ran into trouble. As long as physics dealt only with macroscopic objects, the approximation worked. Once experiments probed deeper, the approximation failed. The failure was not a crisis. It was a signal that a broader framework was needed. There is a historical lesson here. In the 19th century, heat was once thought to be a substance called caloric. Experiments eventually showed that heat is energy in motion, not a material fluid. Mass underwent a similar conceptual transition. It was once treated as a primitive quantity, irreducible and self-explanatory. Relativity and quantum physics revealed that it is emergent from deeper processes. This does not mean that mass is illusory or subjective. It means it is relational. It depends on how energy is organized within a system. When the organization changes, the mass changes. Nuclear reactions demonstrate this dramatically. Chemical reactions demonstrate it subtly. Stellar evolution demonstrates it on cosmic scales. NASA's work in space exploration relies on this understanding in practical ways. When calculating fuel requirements, orbital dynamics, and energy budgets, engineers treat mass and energy consistently. They account for relativistic effects where necessary, not because it is philosophically interesting, but because precision demands it. The success of missions across the solar system is quiet evidence that the mass-energy framework works. The James Webb Space Telescope offers another example. Its detectors measure the energies of incoming photons with extraordinary sensitivity. Those photon energies trace processes that occurred billions of years ago when the universe was young. The telescope itself must be carefully designed so that its own internal energy does not overwhelm the signals it seeks. The entire mission is an exercise in managing energy, mass, and stability in a relativistic universe. Understanding mass as confined energy also reshapes how we think about stability. Matter persists not because it is inert, but because its internal energies are arranged in configurations that resist change. Atoms are stable because electrons occupy specific energy states. Nuclei are stable because the strong force binds quarks into protons and neutrons and binds those into nuclei. Solids are stable because electromagnetic interactions hold atoms in place. Stability is not the absence of energy. It is the presence of energy organized in a way that does not dissipate easily. This view helps explain why the distinction between matter and radiation is less absolute than it appears. Radiation carries energy and momentum, but it does not form stable rest configurations on its own. Matter does, because its interactions allow energy to be trapped. That trapping is what gives rise to rest mass. The scale responds to that trapped energy. Seen this way, E equals m times the speed of light squared is not a slogan. It is a statement about accounting. It tells us how much energy is associated with a given amount of mass when a system is at rest. It does not say that all energy automatically counts as mass. It says that when energy is confined in a rest frame, it manifests as mass. This distinction brings coherence to topics that otherwise feel disconnected. Photons carry energy but no rest mass because their energy is not confined in a rest frame. Protons weigh as much as they do because enormous energy is confined inside them. Your body weighs what it does because countless interactions trap energy in stable arrangements. Carl Sagan once remarked that understanding our place in the universe requires us to accept results that challenge common sense but are supported by evidence. The idea that we have been weighing energy all along is one of those results. It is not meant to diminish the solidity of the world. It is meant to explain it. If mass is energy confined by interactions, then the question shifts from what mass is to how those interactions arose and why they have the strengths they do. Because once energy became capable of confinement, the universe gained the ability to build atoms, stars, and everything that followed. Part 4. How the Higgs field quietly explains the mass of fundamental particles. If mass is not a basic ingredient of nature, then one question refuses to stay quiet. Why do electrons and quarks weigh anything at all? This is where the story turns inward, away from atoms and nuclei, and toward the deepest layer of the Standard Model, where mass does not appear as a substance, but as a consequence of interaction. By the middle of the 20th century, physicists had reached an uncomfortable impasse. Quantum field theory had achieved remarkable success in describing particles and forces, yet it carried a troubling symmetry. According to the equations, many fundamental particles should behave as if they were massless. Electrons, quarks, and even the carriers of the weak force emerged naturally with zero rest mass. But nature disagreed. Experiments showed that electrons have mass. Quarks have mass. The W and Z bosons are heavy. The mathematics was elegant, but reality was heavier. This was not a minor discrepancy. Massless electrons would move at the speed of light. Atoms would not exist. Chemistry would collapse. The universe we observe could not form. Something in the equations had to change, but not in a way that destroyed the symmetries that made the theory work. The solution did not come from adding mass by hand. That approach breaks the mathematical consistency of quantum field theory. Instead, physicists began to suspect that mass might emerge from interaction rather than from intrinsic substance. The idea was radical at the time. It suggested that particles do not carry mass the way they carry charge. They acquire mass through their relationship with something else. In the 1960s, several physicists working independently explored this possibility. Among them were Peter Higgs, François Englert, and Robert Brew. Their insight was subtle but powerful. They proposed that empty space is not truly empty. It is filled with a field that has a non-zero value everywhere. Particles moving through this field interact with it, and that interaction gives rise to mass. This field is now called the Higgs field. It is not a force in the usual sense. It does not pull or push particles through space. Instead, it alters how particles respond to motion. A particle that interacts strongly with the Higgs field resists acceleration more. That resistance is what we measure as mass. This explanation reframes mass in a way that aligns perfectly with relativity. Mass is not an intrinsic lump attached to a particle. It is a measure of how much energy is required to change the particle's state of motion. The Higgs field provides that energy through interaction. Electrons are a clear example. In the Standard Model, an electron begins as a massless excitation of an underlying field. When the Higgs field takes on a non-zero value throughout space, the electron field couples to it. This coupling alters the electron's energy structure. The result is a stable particle with a well-defined rest mass. The mass is not added. It emerges. Quarks behave in the same way, though with different strengths of interaction. Each type of quark couples to the Higgs field with a specific intensity. That coupling determines its mass. This is why quarks span such a wide range of masses, from the very light up and down quarks to the much heavier top quark. The difference is not in their composition, but in how they interact with the Higgs field. This framework preserves the symmetry of the equations while matching observation. It also explains why some particles remain massless. Photons do not interact with the Higgs field. Their equations retain full symmetry, and they remain massless. Gluons, the carriers of the strong force, are also massless at the fundamental level. The pattern is not arbitrary. It follows directly from how fields couple. For decades, this explanation remained incomplete because the Higgs field itself had not been observed. The theory predicted a specific kind of excitation of the field, a particle now called the Higgs boson. Detecting it required energies far beyond what early accelerators could reach. The idea waited, quietly, for technology to catch up. That moment arrived in 2012 at CERN, when the Large Hadron Collider produced data consistent with a new particle at an energy of about 125 giga-electron-volts. Independent experiments using the ATLAS and CMS detectors confirmed the result. The properties of the particle matched those predicted for the Higgs boson with remarkable precision. The field that gives particles mass was no longer hypothetical. NASA and ESA do not operate particle accelerators, but they recognized the significance immediately. The Higgs discovery completed the Standard Model, the framework used to interpret everything from cosmic ray interactions to the behavior of matter in the early universe. Space-based observations rely on particle physics to model processes such as nucleosynthesis, neutrino production, and high-energy radiation from astrophysical sources. The Higgs field became part of that foundation. It is important to understand what the Higgs field does and does not explain. It explains why fundamental particles like electrons and quarks have non-zero rest mass. It does not explain most of the mass of everyday objects. As explored in the previous part, the bulk of the mass of atoms comes from binding energy and internal motion within protons and neutrons. The Higgs field enables quarks to have mass, but the strong force amplifies that contribution dramatically. This distinction matters because it prevents a common misunderstanding. The Higgs field is not responsible for all mass in the universe. It is responsible for allowing certain particles to have mass at all. Once that permission exists, other interactions determine how much mass composite objects acquire. The story behind this discovery also reveals something about how science advances. The Higgs field was not proposed to explain a single anomaly. It emerged from a demand for consistency. Physicists wanted equations that respected symmetry and matched observation. The Higgs mechanism satisfied both. Its success was not guaranteed. It was tested relentlessly against data. When the Higgs boson was discovered, Peter Higgs reportedly said he had not expected to live to see it confirmed. The idea had taken nearly 50 years to move from theory to observation. That timescale reflects the patience built into scientific progress. Nature does not hurry to validate ideas. It waits for careful measurement. The Higgs field also reinforces a theme running through this series. Mass is not a primitive quality stamped onto particles at creation. It is relational. It depends on interaction. Without the Higgs field, electrons would be massless. Without the strong force, protons would be much lighter. Without confinement, nuclei would not hold together. Each layer adds structure and weight. This layered picture resolves an apparent contradiction. If mass is energy, and energy can exist without mass, why do some particles acquire mass, while others do not? The answer is not arbitrary. It is encoded in how fields interact. The Higgs field is one interaction among many, but it plays a special role because it shapes the low-energy universe where atoms form. Astrophysics offers indirect confirmation of this framework. In the early universe, when temperatures were extremely high, the Higgs field did not yet have its present value. Under those conditions, particles behaved as if they were massless. As the universe expanded and cooled, the Higgs field settled into its current state, and particles acquired mass. This transition influenced how matter clumped, how radiation decoupled, and how the first structures formed. Modern cosmological models, used by NASA and ESA to interpret observations of the cosmic microwave background, incorporate this process. The James Webb Space Telescope, while not observing the Higgs field directly, studies galaxies formed hundreds of millions of years after this transition. The fact that such structures exist at all depends on particles having mass. The Higgs field, acting silently across all of space, made that possible. The language used to describe the Higgs field often invites misleading imagery. It is sometimes compared to a medium that slows particles down, but this analogy has limits. The field does not create friction. Particles do not lose energy by interacting with it. Instead, the interaction alters the energy-momentum relationship itself. The particle's response to force changes. That change is mass. Understanding this point requires care, but it rewards patience. The Higgs field does not weigh particles down. It reshapes the landscape in which motion occurs. In that landscape, some paths require more energy to change direction than others. That resistance is what we measure as mass. Carl Sagan once said that science is a way of thinking much more than it is a body of knowledge. The Higgs field exemplifies this. It is not an object you can point to. It is a conceptual structure that makes sense of disparate observations. Its existence is inferred from patterns that repeat with astonishing reliability. This brings us back to the opening question. If mass is not fundamental, why do electrons and quarks weigh something? The answer is not because they are made of a heavier substance. It is because they participate in a field that fills all of space, and that participation carries an energetic cost. The universe charges particles for existing as stable, localized entities. And this realization opens a new direction. If mass arises from interaction with fields, then altering those fields would alter mass itself. That idea is not merely theoretical. It points toward the conditions of the early universe and toward the limits of what physics allows. What matters next is not where those interaction strengths come from, but how their effects show up in ordinary situations. If mass arises whenever energy is held in a stable way, then that rule does not stop at particles and fields. It extends upward into everyday objects, where added energy quietly changes weight in ways we rarely notice. Part 5. Why heating coffee or compressing a spring literally makes them heavier. Can warmth and tension really add weight to the world? Or is this one of those claims that sounds clever until you look closely? Physics answers this question without drama, without metaphor, and without exception. Yes. When you heat a cup of coffee or compress a spring, the system becomes heavier, not by analogy, not by interpretation, but by definition. The increase is small beyond everyday measurement, but it is real, unavoidable, and built directly into how mass is defined in modern physics. This idea is unsettling precisely because it lives so close to daily life. Heating coffee feels ordinary. Compressing a spring feels mechanical and familiar. Neither action seems related to relativity, particle physics, or the structure of space-time. And yet, these quiet actions expose one of the most important consequences of Einstein's work. Mass is not reserved for exotic objects or nuclear reactions. It responds to internal energy everywhere. To understand why, we need to be careful about what mass means in this context. Mass is not a label for solidity or density. It is a measure of how much energy a system possesses when viewed in its own rest frame. If a system can sit still as a whole, then any energy stored inside it contributes to its mass. The form of that energy does not matter. Thermal motion counts. Elastic tension counts. Chemical binding counts. Nuclear binding counts. The universe does not distinguish between them. This principle emerged gradually as physicists learned to treat energy accounting with precision. Early thermodynamics already hinted at it. Heat was once thought of as a substance, something that flowed into objects. Experiments eventually showed that heat is energy associated with microscopic motion. When molecules move faster, temperature rises. That motion carries energy. What took longer to accept is that this energy does not simply disappear into activity. It becomes part of the system's total energy content. Einstein recognized this implication almost immediately after developing special relativity. If energy contributes to inertia, then adding energy must increase mass. He did not need nuclear reactions to see this. He understood that any closed system, warmed or stressed internally, would resist acceleration slightly more than before. Consider a cup of coffee. At room temperature, the molecules in the liquid are already in motion. When you heat the coffee, the molecules move faster. Their average kinetic energy increases. The coffee cup, sitting on the table, is still at rest as a whole, but internally there is more energy than before. According to relativity, that additional energy contributes to the mass of the system. The effect is extraordinarily small. Raising the temperature of a kilogram of water by 1 degree Kelvin adds an amount of energy that corresponds to a mass increase far beyond the sensitivity of household scales. But physics does not care about convenience. The increase exists because the definition demands it. The same logic applies to mechanical energy. Take a spring and compress it. You store elastic potential energy in the spring's structure. The atoms are displaced from their equilibrium positions. Electromagnetic forces resist this displacement. Energy is stored in the configuration. If you place the compressed spring on a scale, the scale reads the gravitational response of the entire system. The stored energy contributes to that response. The compressed spring is heavier than the relaxed one. This is not speculation. It follows directly from the same reasoning that explains nuclear mass defects and particle masses. The difference is scale. Nuclear reactions involve enormous energies packed into tiny spaces, making mass changes detectable. Thermal and mechanical energies involve much smaller energy densities, making mass changes effectively invisible in daily life. But invisibility is not absence. Physicists have tested this principle indirectly for decades. In high-precision experiments, systems with different internal energy states show different inertial behavior. Atomic clocks tick at different rates depending on gravitational potential and motion, reflecting changes in energy and mass consistent with relativity. These effects are small, but they are measured routinely in technologies such as GPS, which NASA relies on for navigation and timing. The reason these everyday examples matter is that they strip away any sense that mass-energy equivalence belongs only to cosmic or subatomic extremes. The equation does not switch on at high energies and switch off in kitchens. It applies everywhere, all the time. This universality is part of what makes relativity unsettling. It does not offer special exemptions for comfort. When you heat an object, you change its internal energy. When internal energy changes in a system that can be at rest, mass changes. That is the entire argument, and it does not rely on exotic assumptions. There is a historical story here that often goes untold. In the early 20th century, some physicists resisted this conclusion because it seemed to blur categories that had been carefully separated. Heat belonged to thermodynamics, mass belonged to mechanics. Elastic energy belonged to materials science. Relativity ignored these boundaries. It unified them under a single accounting rule. This unification forced engineers and scientists to rethink assumptions. In nuclear engineering, the consequences were immediate and dramatic. In everyday engineering, the consequences were subtle but still present. Over time, the framework proved so consistent that it became invisible. Engineers account for energy and mass without consciously invoking Einstein's equation because the principles are built into their models. NASA's spacecraft designs quietly reflect this understanding. When fuel is burned, the mass of the spacecraft changes. When energy is stored in batteries, the mass increases slightly. These changes are negligible for most mission planning, but they are conceptually real. The same physics governs stars and coffee cups. The spring example offers another layer of clarity. A compressed spring stores energy in the electromagnetic fields between atoms. That energy does not reside in motion. The spring can sit perfectly still while holding energy. This is precisely the condition under which energy contributes to mass. The system has more energy at rest than before, so it has more mass. This observation helps dissolve a common misunderstanding. People often associate mass increase with motion, thinking of fast-moving particles gaining mass. Modern physics avoids that language because it confuses frame-dependent effects with invariant properties. The mass increase discussed here is not due to motion relative to an observer. It is due to energy stored internally while the system remains at rest. That distinction matters. The coffee cup does not weigh more because its molecules are moving relative to the table. It weighs more because, in the frame where the cup is at rest, the total energy content is higher. If you could magically stop all molecular motion without removing energy, the mass would remain the same. Motion is not the key. Energy is. This idea also explains why cooling an object reduces its mass. As thermal energy is removed, the total energy content decreases. The mass decreases accordingly. Again, the effect is tiny, but it is symmetrical and consistent. Heating adds mass. Cooling removes it. Elastic systems follow the same rule. Stretch a rubber band, compress a gas, charge a capacitor. In each case, energy is stored. If the system is isolated and at rest, the stored energy contributes to mass. The form of storage does not matter. This realization ties directly back to the deeper themes of this series. Mass is not a substance. It is a measure of energy in a particular condition. Once that is accepted, the everyday examples stop feeling paradoxical and start feeling inevitable. Carl Sagan often emphasized that science reveals the extraordinary hiding in the ordinary. He did not mean that everyday objects are magical. He meant that they are governed by laws that extend far beyond immediate perception. The coffee cup on the table participates in the same framework that governs stars and galaxies. It obeys the same accounting rules. What makes these examples powerful is not their dramatic impact, but their quiet consistency. The universe does not reserve mass-energy equivalents for moments of spectacle. It applies it relentlessly, even when the differences are too small to matter practically. This consistency also protects physics from contradiction. If heating a system did not increase mass, relativity would fail in a subtle way. Energy conservation would break when systems interact gravitationally. The coherence of the theory would unravel. The fact that the theory remains consistent across scales is one of its strongest validations. These ideas have been confirmed repeatedly in high-energy experiments, astrophysical observations, and precision measurements. While no one weighs hot coffee to test relativity, the same principles underpin technologies and observations that are tested every day. The confidence comes from the framework's success everywhere else. The James Webb Space Telescope, for example, must account for thermal energy carefully. Its instruments are cooled to extremely low temperatures, so that their own thermal radiation does not swamp faint signals from distant galaxies. This is not only about photons and detectors. It is about energy management in systems where precision matters. The same energy accounting governs mass, radiation, and stability. Seeing that heating and compression add mass reshapes how mass itself has to be understood. When energy stored inside ordinary systems contributes to weight, mass becomes sensitive to configuration. It depends on how energy is arranged and held together, not only on which particles are present. From that perspective, inertia, gravity, and even space-time begin to look less like properties of matter alone and more like responses to organized energy. But that understanding carries a clear limitation. All of these contributions appear only when the system is treated as being at rest. Once motion enters the picture, the situation changes. Speed adds energy, yet it does not add mass in the same way internal energy does. That distinction is subtle, but it becomes unavoidable at high velocities, where familiar intuitions about movement begin to fail. Part 6. Why motion alone does not add mass, no matter how fast you go. If speed adds energy, then why does the universe refuse to let speed add weight? This question sounds simple, almost obvious, yet it has confused generations of students, engineers, and even physicists, because it exposes a fault line between intuition and the way nature actually keeps its accounts. At first glance, the argument seems irresistible. Push an object harder, make it move faster, and you must be adding energy. If energy and mass are equivalent, then the object should become more massive as it speeds up. Early discussions of relativity often leaned on this intuition, speaking of relativistic mass increasing with velocity. But over time, this language quietly disappeared from serious physics, not because it was forbidden, but because it obscured what mass truly is. To understand why motion alone does not add mass, we have to slow down and return to a concept that Einstein treated with extraordinary care: the reference frame. Every measurement in physics is made from somewhere. Velocity, energy, and momentum all depend on who is doing the measuring. Mass, in its modern definition, does not. Imagine an object moving smoothly through space. From your point of view, it has kinetic energy. From another point of view, moving alongside it, that same object is at rest. Its kinetic energy in that frame is zero. The energy associated with motion vanishes simply by changing perspective. This is not a trick. It is a fundamental feature of relativity. Mass cannot behave like that. If mass changed depending on who observed it, physics would lose its consistency. Atoms would weigh different amounts depending on the laboratory. Stars would have different masses depending on the telescope. Nature does not permit this. The mass of an object must be the same in every inertial frame. That requirement alone rules out kinetic energy as a contributor to mass. Einstein understood this from the beginning. When he introduced the idea that mass is related to energy, he was careful to specify which energy. Not all energy qualifies. Only energy that belongs to a system when it is at rest counts toward mass. This is why the concept of rest energy became central. Rest energy is what remains when motion is removed by choosing the appropriate frame. An object in motion has more total energy than the same object at rest, but that extra energy is not intrinsic. It exists only relative to a chosen frame. Change frames, and the kinetic energy changes. The rest energy does not. Mass is tied to the part of energy that cannot be transformed away. This distinction becomes clearer when we think about internal versus external motion. When you heat an object, as discussed in the previous part, the internal motion of its molecules increases. But there is no reference frame in which all that internal motion disappears simultaneously. The object can be at rest as a whole, yet its internal energy remains. That energy is trapped. It contributes to rest energy. It adds mass. By contrast, when you throw a ball, its motion is external. There exists a frame where the ball is not moving at all. In that frame, the kinetic energy is gone. Because that energy can be eliminated by changing perspective, it does not qualify as mass. This is not an abstract distinction. It is enforced every day in particle accelerators. At CERN and other facilities, particles are accelerated to speeds extremely close to the speed of light. Their energies increase dramatically. Their momenta increase. Their behavior changes, but their rest masses remain exactly the same. An electron accelerated to high energy does not become a heavier electron in its own rest frame. It remains an electron with the same invariant mass. NASA relies on this distinction when modeling cosmic rays and high-energy particles encountered by spacecraft. Particles arriving at near-light speeds carry enormous kinetic energies, yet their rest masses remain unchanged. The interaction outcomes depend on total energy and momentum, but the identity of the particles does not. The temptation to say that fast objects become more massive comes from a desire to preserve familiar formulas. In early treatments, physicists sometimes defined a velocity-dependent mass so that Newton-like equations would continue to work. This relativistic mass increased with speed. While mathematically consistent, it shifted the meaning of mass from an invariant property to a frame-dependent quantity. Over time, this approach was abandoned because it created more confusion than clarity. Modern relativity keeps mass invariant and assigns speed-dependent effects to energy and momentum instead. This choice preserves the deep symmetry of the theory. It also aligns with how nature behaves. A simple thought experiment illustrates the problem with motion-based mass. Imagine two identical spacecraft drifting in deep space, far from gravity. One fires its engines and accelerates relative to the other. From the perspective of the first craft, it is now moving and has kinetic energy. From the perspective of the second craft, the roles are reversed. Each sees the other as moving. If motion added mass, then each observer would conclude that the other craft has gained mass while their own has not. That contradiction cannot be resolved without abandoning the idea that mass is intrinsic. Relativity resolves it cleanly by separating energy into parts. Total energy depends on the frame. Rest energy does not. Mass is tied to rest energy alone. This is why the phrase, "moving objects gain mass," is misleading. Objects gain energy when they move relative to a chosen frame. They do not gain mass in any absolute sense. The resistance to acceleration that we associate with mass remains the same in the object's own rest frame. The distinction also clarifies why photons behave so differently. Photons always move at the speed of light. There is no frame in which they are at rest. All of their energy is kinetic in nature. Because that energy cannot be transformed into rest energy, photons have no mass. This is not a special exemption. It is the same rule applied consistently. Einstein addressed this issue directly in his later writings, cautioning against confusing energy with mass. In one discussion, he emphasized that the mass of a body is not a measure of its energy content, but rather of the energy it possesses when at rest. The words are careful, and they matter. Everyday experience makes this distinction hard to accept, because we rarely change frames consciously. We live in one frame, tied to Earth, and we treat motion as absolute. Relativity teaches us that motion is relational. Once that lesson is absorbed, the idea that motion alone does not add mass becomes unavoidable. Consider a more subtle example. A sealed box contains a bouncing particle. The particle moves back and forth inside the box. From the outside, the box can be at rest. The internal motion cannot be transformed away. The energy of that motion contributes to the mass of the box. If you stop the particle, converting its kinetic energy into heat, the mass remains the same. The form of internal energy changes, but it remains internal. Now consider the same box moving through space as a whole. That motion can always be removed by choosing a frame moving alongside the box. The box's mass does not depend on whether it is drifting or stationary relative to a distant observer. The internal energy does. The external motion does not. This reasoning extends all the way to the larger scales. Galaxies move relative to one another. Clusters move within the expanding universe. Yet when astronomers measure masses, they do not include bulk motion as mass. They include energy that is gravitationally bound and cannot be transformed away by a simple change of frame. NASA and ESA use this framework when modeling galaxy clusters and gravitational lensing. The mass inferred from gravitational effects corresponds to rest energy and bound energy, not to the random velocities of galaxies within the cluster. Motion contributes to pressure and dynamics, but not to mass itself. The same principle appears in thermodynamics. Temperature measures average kinetic energy of particles relative to a frame where the system as a whole is at rest. That energy is internal. It cannot be removed by changing frames without introducing motion of the entire system. That is why thermal energy contributes to mass. Bulk motion does not. This distinction also protects the principle of energy conservation. If motion alone added mass, then accelerating an object and then decelerating it in different frames would lead to paradoxes where mass appeared and disappeared depending on perspective. Relativity avoids this by assigning frame-dependent energy to motion and frame-invariant mass to rest energy. The calmness of this solution is part of its strength. There is no special rule for fast objects. There is no exception for everyday ones. The same accounting applies universally. Carl Sagan often reminded audiences that science succeeds not by satisfying intuition, but by insisting on coherence. The refusal to let motion add mass is one such insistence. It feels counterintuitive because it forces us to abandon the idea that speed is absolute. But once that idea is gone, the rest follows naturally. This understanding also reshapes how we think about inertia. Inertia is not resistance to motion in general. It is resistance to changes in motion measured in the rest frame of the object. That resistance is encoded in mass. Changing frames does not change inertia. Changing internal energy does. Experiments have confirmed this distinction in countless ways. Particle physics experiments show invariant masses independent of beam energy. Precision measurements of atomic transitions show mass shifts due to internal energy changes, not due to motion. Astrophysical observations show consistent mass estimates regardless of relative velocities. Even technologies that seem far removed from relativity rely on this principle. GPS satellites must account for relativistic effects on time and energy. Their motion relative to Earth affects clock rates, but it does not change the intrinsic masses of the atoms in their clocks. Engineers separate frame-dependent effects from invariant properties with care, because accuracy demands it. Understanding why motion alone does not add mass reshapes how several familiar facts fit together. It accounts for why heating a system increases its mass, while simply throwing it faster does not. It clarifies why protons possess mass, while photons do not, even though both carry energy. In this framework, energy and mass are related through rest energy, but they do not behave as interchangeable quantities in every situation. That distinction becomes unavoidable once rest energy enters the picture. Mass depends on it, and rest energy depends on the existence of a rest frame. Ordinary matter always provides one. Light does not. When a system offers no rest frame at all, the usual rules for assigning mass quietly fail, and this is precisely where most attempts to calculate a photon's mass go wrong. Part 7. The fatal mistake everyone makes when calculating a photon's mass. What if the problem has never been Einstein's equation, but the way we insist on forcing it to answer a question it was never meant to solve? This single misstep, repeated endlessly in textbooks, forums, and casual explanations, is responsible for most of the confusion surrounding photon mass, and once you see it clearly, the mystery collapses into something precise, restrained, and deeply consistent. The mistake usually begins innocently. A photon has energy. That energy can be measured. It heats detectors, triggers chemical reactions, pushes solar sails, and leaves unmistakable signatures in telescopes operated by NASA and ESA. If energy and mass are equivalent, then it feels natural to take the photon's energy and divide it by the square of the speed of light. A number comes out. The calculation looks clean. The conclusion seems unavoidable. The photon has mass. But physics does not ask whether a number can be produced. It asks whether that number represents a real, invariant property of nature. And this is where the error becomes decisive. Einstein's equation linking mass and energy was never a universal conversion rule. It does not say that all energy is mass, or that mass can be assigned to anything energetic by simple arithmetic. It applies to a specific kind of energy that belongs to a system when it is at rest. This condition is not a technicality. It is the core of the definition. A photon has energy, but that energy is inseparable from its motion. There is no experiment, no observation, and no valid reference frame in which a photon is at rest. Every attempt to assign a mass by dividing photon energy by the square of the speed of light silently assumes a rest frame that does not exist. This assumption is rarely stated, but it is always there. To see why this matters, it helps to recall how mass is defined in modern relativity. Mass is not a measure of total energy, as seen by an arbitrary observer. It is a measure of rest energy, the energy a system possesses when all motion relative to the observer has been removed. For an electron, this is straightforward. For a proton, it is straightforward. For a cup of coffee sitting on a table, it is straightforward. For a photon, it is impossible. Photons never stop. They do not slow down. They do not offer a frame in which their energy can be examined without motion. As discussed in earlier parts, this is not a limitation of technology. It is a structural feature of space-time itself. The distinction becomes clearer when we compare photons to systems where dividing energy by the square of the speed of light does make sense. Consider a compressed spring. The spring can be at rest as a whole. The energy stored in its compression remains even when there is no motion. That energy contributes to the mass of the system. Dividing by the square of the speed of light yields a meaningful mass increase because the system has a rest frame. The same is true for a heated object. Thermal energy persists in the rest frame. It cannot be transformed away by changing perspective. That is why it contributes to mass. Now compare this to a photon. Its energy exists only as motion. Change reference frames, and the energy changes. Move toward the photon, and its energy decreases. Move away, and its energy increases. There is no frame in which the photon's energy settles into a fixed, observer-independent value that could qualify as rest energy. If mass depended on total energy rather than rest energy, then mass itself would depend on who was measuring it. One observer would assign a different mass to the same photon than another. Physics cannot allow that. Invariant quantities must remain invariant. Einstein understood this clearly. In his later writings, he repeatedly cautioned against careless interpretations of mass. In one discussion, he emphasized that it is better to speak only of rest mass, because introducing other mass concepts leads to confusion without adding insight. His concern was not philosophical. It was practical. He saw how easily equations could be misused. The history of this confusion is instructive. In the early days of relativity, physicists were still developing intuition for how energy and momentum behave at high speeds. Some introduced the idea of velocity-dependent mass as a way to preserve familiar Newtonian forms. Under that scheme, fast-moving particles were said to gain mass. Photons, moving at the ultimate speed, were sometimes described as having an effective mass. This language lingered for decades. It was never entirely wrong, but it was deeply misleading. Over time, as the energy-momentum framework of relativity became standard, the language shifted. Modern physics abandoned relativistic mass not because it was mathematically inconsistent, but because it obscured the invariant structure that makes relativity work. That shift matters enormously for photons. If you define mass as total energy divided by the square of the speed of light, then photons appear massive. If you define mass correctly, as invariant rest energy, photons are exactly massless. Observations support the latter definition with extraordinary precision. If photons had even a tiny rest mass, electromagnetic theory would change. Maxwell's equations would be modified. Electric and magnetic fields would behave differently at large distances. Radio waves would attenuate in ways not observed. The speed of light would depend on frequency. Lower energy photons would travel slightly slower than higher energy ones. Astronomers have searched for these effects for decades. They have not found them. Signals from distant astrophysical events, including gamma-ray bursts and supernovae, arrive across wide energy ranges with timing consistent with massless propagation. The James Webb Space Telescope observes light that has traveled for more than 13 billion years. If photons carried rest mass, tiny delays would accumulate over such distances. They do not appear. NASA and ESA rely on this consistency. Space communication, deep space navigation, and astrophysical modeling all assume massless photons. These assumptions are not conveniences. They are conclusions drawn from data. Another way to see the error is to consider how photons interact gravitationally. Light bends in gravitational fields. Gravitational lensing maps, used extensively by NASA and ESA to study dark matter and large-scale structure, rely on the fact that photons follow curved paths in spacetime. This bending does not require mass. It requires energy and momentum interacting with spacetime geometry. General relativity treats energy, momentum, pressure, and stress as sources of gravity. Photons contribute to gravity through their energy, not through mass. This distinction is subtle but essential. Assigning a rest mass to photons would double count their gravitational influence and break the theory's internal consistency. The temptation to assign mass to photons often arises from a desire for symmetry. Matter has mass. Radiation has energy. It feels tidy to say radiation also has mass, but physics does not prioritize tidiness. It prioritizes coherence. Coherence demands that mass be tied to rest energy. Once that rule is applied consistently, photons fall into place naturally. They are energetic, they are dynamic, they are influential. They are massless. This does not make them less real. In fact, it makes them more sharply defined. The fatal mistake, then, is not a computational error. It is a conceptual one. It is the mistake of forgetting to ask which energy qualifies. Dividing by the square of the speed of light without checking whether rest energy exists is like measuring the depth of a shadow and calling it a height. This mistake persists partly because it produces a number, and numbers feel authoritative. But physics is not impressed by numbers divorced from definitions. It demands that quantities mean the same thing everywhere, to everyone, under all conditions. Carl Sagan often reminded his audience that extraordinary claims require extraordinary evidence. The claim that photons have mass is not extraordinary because it is bold, but because it contradicts a framework that has survived a century of testing. The evidence does not support it. Once the error is removed, the picture becomes calmer, not more complicated. Photons carry energy and momentum. They influence matter and space-time. They remain massless because they have no rest energy. E equals mass times the square of the speed of light remains correct, but it speaks only to systems that can be at rest. This clarity also explains why discussions of photon mass often feel circular. They bounce between energy and mass without addressing the missing ingredient, the rest frame. Without that frame, the concept of mass has nowhere to attach. Understanding this does not require advanced mathematics. It requires patience with definitions. It requires resisting the urge to simplify too far. When those conditions are met, the confusion dissolves. At this point, the constraint becomes unavoidable. If mass requires rest energy, and rest energy requires a rest frame, then anything that moves at the speed of light cannot possess mass. This is not a special rule written for photons. It follows directly from how mass is defined, and its consequences extend far beyond light itself. Once photons are understood to be massless by necessity rather than by exception, speed takes on a different role. It is no longer just a way of describing motion. It becomes a limit built into how causes and effects can be connected. Part 8. Why you can never catch up to a photon, even in thought experiments. What happens when physics does not merely forbid an experiment, but forbids the very idea behind it? This is the strange position light occupies in our universe. You can chase a photon in imagination, accelerate alongside it in equations, or construct the most careful thought experiment ever devised, and still, you will never arrive at a frame in which the photon is at rest. The universe does not block this attempt with technical difficulty. It blocks it with principle. This story begins with one of the most radical statements ever made about nature, a statement so simple that it hides its severity. The speed of light in vacuum is the same for all observers, regardless of their motion. This is not a hypothesis tested once and set aside. It is the foundation of special relativity, confirmed by more than a century of experiments, from early interferometers to modern satellite navigation systems operated by NASA and ESA. At first, this sounds like a rule about measurement. Look carefully, and it becomes a rule about existence. If the speed of light is the same for all observers, then there can be no observer who measures light as stationary. No matter how fast you move, light still recedes from you at the same speed. There is no loophole, no privileged frame, no hidden reference point where the rule relaxes. Einstein recognized immediately that this statement would overturn classical ideas of motion. In Newtonian physics, speeds add. If you run toward a moving object, you expect to close the gap. Relativity breaks this expectation. Velocities combine in a way that preserves the speed of light as an absolute limit. As you accelerate, distances contract and time dilates, adjusting themselves so that light's speed remains unchanged. This adjustment is not cosmetic, it is structural. Space and time reshape themselves to enforce the rule. The closer you approach the speed of light, the more extreme these effects become. Time slows relative to distant observers. Lengths contract along the direction of motion. Energy increases without bound. Yet, the speed of light remains unmoved. This leads to a crucial consequence. If you imagine riding alongside a photon, you imagine a frame where the photon is at rest. But special relativity does not allow such a frame to exist. To reach it, you would need to move at the speed of light. To move at the speed of light, you would need infinite energy. This is not a limitation of engines or materials. It is a boundary written into the geometry of space-time. Particle accelerators make this boundary visible. At CERN and other facilities, electrons are accelerated to speeds extremely close to the speed of light. As their speed increases, their energy grows enormously, but the speed itself changes less and less. Each additional unit of energy produces a smaller increase in velocity. The particle asymptotically approaches the speed of light, never reaching it. NASA observes similar effects in cosmic rays, particles arriving at Earth with energies far exceeding those produced in laboratories. Some travel at speeds so close to light speed that the difference would be measured in parts per trillion, yet none exceed the limit. None reach it. None cross into a photon-like state. This is not because photons are special in a mysterious way. It is because photons occupy a different category entirely. Massive particles can approach the speed of light, but never arrive. Photons are not approaching it. They are born there. This difference explains why photons cannot be observed at rest. It is not that we lack the right experiment. It is that the concept contradicts the structure of space-time. There is no transformation that takes you into the photon's frame, because such a transformation would require breaking the rule that defines relativity itself. Once this is understood, the connection to mass becomes unavoidable. Mass, as used in modern physics, is defined through rest energy. Rest energy is what remains when motion is removed by choosing the appropriate frame. If no rest frame exists, no rest energy exists. Without rest energy, mass vanishes. This is not an additional assumption layered onto relativity. It is a direct consequence. Photons are massless, not because we choose to define them that way, but because the universe leaves no alternative. The phrase photon rest energy appears occasionally in confused discussions, but it names something that cannot exist. Photons have energy, but that energy is inseparable from motion. It is always kinetic in character. Change frames, and the measured energy changes. There is no invariant energy left behind when motion is removed, because motion cannot be removed. This frame dependence is essential. Consider two observers moving relative to one another, both measuring the same photon. One measures a higher energy, the other a lower one, depending on their motion relative to the photon's direction. Both measurements are correct. Both are consistent with relativity. If mass were defined by total energy, these observers would disagree about the photon's mass. Physics cannot tolerate that kind of ambiguity. By tying mass to rest energy, relativity preserves consistency. Quantities that must be invariant remain invariant. Quantities that depend on motion are allowed to change. Photons fit perfectly into this structure. Observations reinforce this picture relentlessly. If photons had rest mass, their speed would depend slightly on energy. Lower energy photons would travel more slowly than higher energy ones. Over long distances, the difference would accumulate. Astronomers would see energy-dependent delays from distant sources. They do not. NASA, ESA, and other observatories monitor signals from supernovae, pulsars, and gamma-ray bursts across wide energy ranges. Light from these events travels for millions or billions of years before reaching Earth. The arrival times match predictions for massless propagation to extraordinary precision. Any deviation would stand out clearly. None have been confirmed. The James Webb Space Telescope adds another layer of evidence. Webb observes infrared light emitted when the universe was very young. These photons have traveled through expanding space for more than 13 billion years. Their behavior is consistent with light that always moves at the same speed in vacuum, independent of energy. This consistency would be impossible if photons carried rest mass. The gravitational behavior of light tells the same story. Light bends in gravitational fields. It orbits black holes. It traces the structure of space-time around massive objects. General relativity explains this without assigning mass to photons. Light follows null paths in curved space-time. Its trajectory is determined by geometry, not by weight. If photons had rest mass, their gravitational behavior would differ in measurable ways. Lensing patterns would change. Orbital paths near compact objects would deviate. Precision measurements have found no such deviations. This is why physicists do not say that photons are almost massless. They say they are massless. The difference matters. Almost would imply a rest frame exists in principle, even if inaccessible. Massless means no such frame exists at all. Einstein understood the severity of this distinction. In discussing the speed of light, he emphasized that it is not merely a large speed, it is a limiting speed. It separates what can be brought to rest from what cannot. Massive particles live on one side of the boundary. Photons live exactly on the boundary itself. This boundary has consequences beyond photons. It defines causality. No signal, no influence, no transfer of information can travel faster than light. This is not an engineering limit. It is a structural limit that protects the order of cause and effect. Photons, by moving at this limit, reveal the framework rather than violating it. They show us where space-time draws its lines. The inability to catch up to a photon, even in imagination, is not a failure of creativity. It is a success of physical law. Thought experiments are powerful tools, but they must obey the same constraints as experiments in the laboratory. When a thought experiment demands a rest frame for light, it demands something space-time does not provide. This realization also clarifies why attempts to assign mass to photons feel persistently unsatisfying. They rely on smuggling in a forbidden frame. Once that frame is removed, the argument collapses. Carl Sagan often spoke about how the universe reveals itself through constraints as much as through possibilities. The speed of light is one of those constraints. It tells us not only how fast signals can travel, but which concepts make sense and which do not. Photons exist as messengers that can never pause. Their energy is always in motion. Their influence is always active. Their lack of rest mass is not a missing feature. It is the feature that allows them to play their role. The speed of light takes on a very different meaning once rest frames are taken seriously. It is not simply the speed at which photons travel, but a boundary no physical system can step beyond. Because of that, its role reaches far past optics or illumination. It defines how cause and effect are allowed to move through the universe at all. When no rest frame exists above a certain speed, the limit stops being about light in particular. It becomes a statement about motion itself and about which descriptions of mass still make sense when that limit is approached. That realization is precisely why one seemingly reasonable idea had to be set aside. Part 9. why physicists abandoned relativistic mass despite it seeming logical. Why did an idea that once appeared in textbooks, lectures, and even Nobel-era discussions quietly fade from modern physics without a formal rejection? Relativistic mass did not disappear because it was dramatically disproven. It disappeared because over time physicists realized it was answering the wrong question, and worse, it was asking students to misunderstand what mass is meant to represent. In the early decades after Einstein introduced special relativity, physicists were struggling with a genuine problem. Newton's equations worked beautifully at everyday speeds, but they broke down as objects approached the speed of light. Energy increased faster than intuition allowed. Momentum behaved strangely. Rather than abandoning familiar forms, some physicists chose a different strategy. They kept Newton-like equations by allowing mass itself to depend on speed. In this picture, an object moving faster simply became more massive. As its speed increased, its relativistic mass increased. At the speed of light, the mass would become infinite, neatly explaining why no object could ever reach that speed. The idea felt clean. It felt mechanical. It preserved older intuitions. For a time, it worked well enough to be useful. Richard Feynman, whose teaching shaped generations of physicists, occasionally used this language in early lectures when building intuition. He was not endorsing it as a fundamental truth. He was using it as scaffolding. But scaffolding has a way of being mistaken for the building itself, especially when it makes calculations look familiar. The trouble began when physicists pushed deeper. Relativity is not merely a correction to Newtonian mechanics. It is a restructuring of how space, time, energy, and momentum relate to one another. In this structure, mass plays a very specific role. It is not a measure of how hard something is to push in a particular frame. It is an invariant quantity, the same for all observers, regardless of how fast they are moving relative to one another. Relativistic mass violated that principle immediately. If mass increased with speed, then mass depended on the observer. One observer would say an object had one mass, another would say it had a different one. Physics can tolerate frame-dependent quantities. Velocity is frame-dependent. Energy is frame-dependent. But mass cannot be, without losing its meaning. This inconsistency did not show up as an error in experiments. It showed up as confusion in interpretation. Consider two observers watching the same particle. One observer sees it moving slowly, the other sees it moving quickly. Under the relativistic mass idea, they must assign different masses to the same particle. Which one is correct? Both. And that answer is precisely the problem. Mass was supposed to identify what the object is, not how it looks from a particular point of view. As relativity matured, physicists recognized that the true invariant structure lay not in force equals mass times acceleration, but in the energy-momentum relationship. Energy and momentum form a unified object that transforms cleanly between frames. Mass emerges from that structure as something that does not change. Once this was understood, relativistic mass became unnecessary. All of the correct predictions could be made using invariant mass, while assigning speed-dependent behavior to energy and momentum instead. The mathematics became simpler. The concepts became cleaner. This shift was not abrupt. It happened gradually, through teaching, through research, through generations of physicists noticing that explanations became clearer when relativistic mass was avoided. Einstein himself expressed discomfort with velocity-dependent mass. In correspondence and later writings, he emphasized that introducing multiple mass concepts created confusion without adding insight. He preferred to speak of rest mass alone, leaving all speed dependence to energy and momentum. The difference may seem subtle, but it has profound consequences. Take the example of a fast particle in an accelerator. Under the relativistic mass idea, the particle becomes harder to accelerate because its mass increases. Under the modern view, the particle becomes harder to accelerate because adding energy produces diminishing returns in velocity as the speed of light is approached. The resistance is not because the particle has become heavier in some intrinsic sense. It is because space-time geometry limits how velocity responds to added energy. Both descriptions predict the same experimental outcomes, but one misleads intuition. Relativistic mass encourages the idea that motion itself creates substance. That speed turns into weight. This intuition breaks down completely when applied to photons. Photons always move at the speed of light. If relativistic mass were taken seriously, photons would have infinite mass. That is not a small inconsistency. It is a catastrophic one. To avoid this, proponents of relativistic mass often introduced special exceptions for light. Photons were said to have relativistic mass but no rest mass, or they were said to have effective mass. Each patch solved one problem while creating another. Modern physics does not need these patches. By defining mass as invariant rest mass, photons fall into place naturally. They have no rest frame. They have no rest energy. Their mass is zero. Their energy and momentum remain real, measurable, and influential. Nothing breaks. This clarity becomes essential in fields like astrophysics and cosmology, where multiple reference frames coexist naturally. NASA and ESA routinely analyze particles, radiation, and massive objects across vast ranges of speed and scale. When modeling cosmic rays, gravitational lensing, or high-energy astrophysical processes, invariant quantities provide a stable foundation. Frame-dependent quantities are handled carefully, but mass is kept fixed. Gravitational physics makes the problem even sharper. In general relativity, gravity responds to energy, momentum, and pressure, not just mass. If relativistic mass were treated as the source of gravity, the theory would double count energy contributions and produce incorrect predictions. Instead, relativity uses the full energy-momentum description, where mass appears only as rest energy. This is not a philosophical preference. It is required for consistency. The quiet abandonment of relativistic mass reflects a broader pattern in science. Ideas are not always discarded with fanfare. Sometimes they fade because better language emerges. Students learn a clearer framework. Textbooks simplify. The older idea becomes optional, then unnecessary, then confusing. By the late 20th century, most advanced physics texts had stopped using relativistic mass entirely. They spoke of invariant mass, total energy, and momentum. Relativistic mass survived mainly in popular explanations and introductory contexts where it seemed intuitive. But intuition is not the same as understanding. Carl Sagan often emphasized that science advances by refining its questions. When a concept persists only because it feels familiar, it eventually yields to one that explains more with less. Relativistic mass explained some effects, but invariant mass explained them all without contradiction. The debate was not settled by authority. It was settled by coherence. When students were taught invariant mass, they made fewer conceptual errors. They understood photons more clearly. They understood why heating adds mass while motion does not. They understood why energy can be enormous without changing what an object fundamentally is. Relativistic mass, by contrast, encouraged a fragmented view. Objects seemed to change their identity depending on speed. Light seemed exceptional rather than natural. Definitions blurred. The simplicity that won was not superficial. It was structural. Once mass was defined as rest energy, all the pieces aligned. Energy could be added without redefining what an object is. Motion could change energy without changing identity. Photons could exist without mass. The speed of light could remain an absolute limit without invoking infinite weights. This shift also prepared physics for deeper theories. Quantum field theory, the Standard Model, and modern cosmology all rely on invariant mass. Particles are classified by their invariant properties, not by how fast they happen to be moving. The Higgs field, discussed earlier, gives particles rest mass. It does not give them relativistic mass. Their interaction with the Higgs field defines what they are, not how they move. Relativistic mass had no place in that framework. So why did it seem logical for so long? Because it preserved older equations and appealed to mechanical intuition. But intuition trained in one framework does not always survive a deeper one. The abandonment of relativistic mass was not an admission of error. It was an act of refinement. Physics learned to say less, more precisely. When mass is required to remain invariant, and light is understood to be massless because it offers no rest frame, the role of the speed of light changes quietly but decisively. It is no longer just a number attached to motion. It marks the boundary between systems that can possess mass and those that cannot. With that boundary in place, nothing new needs to be added. The structure is already complete. Part 10. Why the speed of light is really the speed of causality. What if the most famous speed in the universe was never about light at all, but about the deepest rule that keeps reality from tearing itself apart? This idea feels unsettling at first, because we grow up thinking of the speed of light as a property of illumination, of stars, of photons racing through space. Yet modern physics reveals something far more fundamental. The constant we call the speed of light is the speed at which cause and effect are allowed to connect. It is the ultimate limit that protects the order of events, and everything that reaches this limit must obey rules far stricter than intuition allows. To understand this, it helps to step back from light itself and return to the foundations of special relativity. Einstein did not begin by asking how fast light travels. He began by asking how different observers can agree on the order of events. If two events are separated in space, and one appears to cause the other, then all observers must agree on which came first. Without this agreement, the notion of causality collapses. The remarkable discovery of relativity is that preserving causality requires a universal speed limit. Signals, influences, and information cannot propagate arbitrarily fast, or else different observers would disagree about cause and effect. One observer could see an effect occur before its cause. Physics cannot tolerate that. The speed of light emerges as the boundary that prevents such contradictions. This boundary is not enforced by technology or material strength. It is enforced by space-time itself. Space and time rearrange their measurements so that no observer ever sees a causal influence exceed this speed. When you move faster relative to something else, time slows and distances contract in precisely the way needed to preserve the limit. The equations do not negotiate. They compensate. Photons occupy a unique position in this structure. They move exactly at this causal limit. They do not approach it. They do not cross it. They live on it. This is why they cannot have mass. As we have seen throughout this series, mass requires a rest frame. A rest frame requires speeds below the causal limit. At the causal limit, the concept of rest dissolves completely. This is not an arbitrary rule imposed on light. It applies to anything that might try to move at that speed. If an object had mass, even an infinitesimal amount, it would require infinite energy to reach the causal limit. That requirement is not a flaw in the equations. It is how the equations enforce causality. Seen this way, photons are not strange exceptions. They are indicators. They reveal where the boundary lies. General relativity deepens this picture. In Einstein's theory of gravity, space-time is not a passive stage. It responds to energy and momentum. Light follows paths determined by space-time geometry. It bends around stars. It orbits black holes. It traces the structure of the universe on the largest scales. Yet, even in the presence of extreme gravity, the causal limit remains intact. Light's local speed is always the same. NASA and ESA rely on this consistency constantly. Gravitational lensing measurements, used to map dark matter and galaxy clusters, assume that light follows null paths dictated by space-time curvature, not by mass. The success of these maps, confirmed across independent observations, is a quiet affirmation that light is obeying the rules of causality, not breaking them. The James Webb Space Telescope offers a striking illustration. Webb observes photons emitted when the universe was young, before galaxies like our own had fully formed. These photons have traveled for more than 13 billion years through an expanding cosmos. Along the way, space itself has stretched, altering their wavelengths. Yet at every local point along their journey, the photons moved at the same causal speed. Expansion did not let them outrun causality. It merely changed the scale of space between events. This distinction matters. Sometimes people imagine that cosmic expansion allows galaxies to separate faster than light. In a limited sense, distances can increase faster than light because space itself is expanding. But no object moves through its local spacetime faster than the causal limit. No signal outruns cause and effect. The structure holds. This is why physicists increasingly describe the speed of light as the speed of causality. It is the maximum speed at which information can propagate. It is the speed that separates events that can influence each other from those that cannot. In spacetime diagrams, it defines the light cone, the boundary between the possible and the forbidden. Anything inside the light cone can be causally connected. Anything outside cannot. Photons trace the surface of this cone. Massive objects remain inside it. They can approach the surface, but never reach it. This picture also explains why attempts to exceed the speed of light lead to paradoxes rather than breakthroughs. Faster-than-light signals would allow effects to precede causes in some frames. Closed loops of causality would become possible. Physics would lose its predictive power. The equations of relativity prevent this not by decree, but by structure. Einstein understood this deeply. Although he is often quoted for his equations, his true insight lay in recognizing that the laws of physics must look the same to all observers, and that causality must be preserved. The speed of light emerged as the constant that makes those demands compatible. Carl Sagan once described science as a way of understanding not only what is possible, but what is not. The speed of causality is one of those boundaries. It tells us where explanation must stop and acceptance must begin. Photons, then, are not merely carriers of light. They are carriers of causal connection. When a star explodes, when a galaxy forms, when a detector on Earth registers a signal, photons are the messengers that connect those events across spacetime without violating the order of cause and effect. Their masslessness is essential to this role. If photons had mass, they would move more slowly. Their speed would depend on energy. The causal structure of spacetime would fracture. Different photons would define different causal limits. The universe would lose coherence. Instead, the universe chooses a single limit and enforces it everywhere. Photons reveal that limit by saturating it. This understanding also brings closure to the journey we have taken through energy and mass. We began by asking why photons carry energy without mass. We explored how mass arises from rest energy, from binding, from interaction, from fields like the Higgs. We saw why motion does not add mass, why photons have no rest frame, why attempts to assign them mass fail, and why older concepts like relativistic mass were set aside. Now we see why all of those pieces fit together. They are consequences of a deeper rule. Causality must be preserved. The speed that enforces it must be invariant. Anything that reaches that speed cannot have mass. Anything with mass cannot reach that speed. This rule is not imposed from outside. It is written into the geometry of space-time itself. Modern physics continues to test this structure relentlessly. Experiments search for tiny violations of Lorentz invariance, the symmetry underlying relativity. Astronomical observations look for energy-dependent variations in light speed. So far, the universe has been unwavering. Every test reinforces the same picture. NASA's most precise clocks, flown on satellites and compared across orbits, confirm relativistic time dilation exactly as predicted. ESA's missions mapping the cosmic microwave background rely on photons preserving causal structure across cosmic history. Particle accelerators probe energies where deviations might appear. None have been confirmed. This consistency does not make physics dull. It makes it trustworthy. Understanding the speed of light as the speed of causality also reframes the role of photons in a quieter, more grounded way. They are not rebels outrunning the universe's rules. They are the standard by which those rules are set. Light does not break reality. It reveals its architecture. And that realization allows the story to come to rest without unresolved tension. The questions we asked were not about loopholes or exceptions. They were about coherence. Why does light behave the way it does? Why does mass arise where it does? Why does speed matter in the way it does? The answers converge here. The universe protects cause and effect with extraordinary care. Everything else follows. If you are listening late, perhaps after a long day, it is worth letting this settle without effort. The laws we have traced are not fragile constructions. They have endured every test we know how to perform. They operate quietly, reliably, whether we notice them or not. And as this journey reaches its end, there is no need to carry the questions further tonight. The photons that brought this story to you have done their work, moving at the same speed they always do, connecting one moment to the next. May the same structure that keeps the universe consistent allow your thoughts to slow, your breathing to ease, and your rest to come naturally. Good night.